but not in linked invariants, so it'll be fine.
It's a pleasure to introduce Gong from Texas A&M University, who will tell us about concordance invariants from instantons.
Okay, which is a special case of not in link invariance. So
Okay.
it's okay then. Yes. Okay. So yeah, thank you so much for inviting me. I'm really happy to be here. So I'm going to be telling you about some not in link invariants. I wasn't really sure how much like topology background people would have, so I kind of did like some of the topology stuff very like, sort of in a lot of in like somehow more detailed certainly than I would for a topology audience. So I hope I'm not going to bore you, but so we're going to talk about not in link invariants from instantons. So let me first just sort of go over what a knot in a link is. So a knot is an embedding of a circle in a three-dimensional space. Usually we're going to be doing S3, though it doesn't have to be. And a link is an embedding of some number of circles. Could be 0, could be like 1 or so here are some of the smallest knots counted by number of crossings. A specific kind of knot that I'll be talking about are torus knots, which are basically they're sort of, it's basically you're sort of evenly wrapping a string around a torus. So in these pictures, I think, at least for the larger ones, you can kind of see the torus, right? And you're wrapping a string around it. Is there chalk? Oh, yes, okay. So, and like, I guess like another way you can sort of think about a torus knot, I don't know if this is like preferable to you, but like I'll be sort of using this definition later in this talk, is you can think of, so these are knots in S3, right? And S3 is the boundary of a B4. So you can think of it at, you can think of your B4 sitting inside C2 as being around the origin, and then a torus knot, like an MN torus link, is when you take the intersection of x to the m equals y to the n, this equation, this equation intersected with your S3. So in a knot that is of the form some equation, some like polynomial equation intersected with S3 is going to be called an algebraic knot. And so a torus knot is an example of, well, these are actually torus links unless M and M are relatively prime, but that's an example. Okay, so what I want to talk about are some knot invariants. There are basically like, people say two kinds of knot invariants. So they're the kinds that are easy to define, but hard to compute. So an example of that is like what's called the smooth four-ball genus, which basically says if you have your knot, right, it's sitting in S3, which is a boundary of B4. So you can ask the question, if I take my knot, like what kinds of surfaces inside the B4 can it bound? So this is a little bit different from the Seifert surface that Allison was telling you about, because the Seifert surface is sitting in S3, right? But here we're allowed to sort of go into the B4. And then for like surfaces like this, you can ask similarly to the question you could ask with Seifert surfaces, which is what can their genus be? It's pretty easy to see that if you can find something of genus G, then you can find something of genus G plus 1 by just sort of adding a little, you know, tiny little torus to it. So with the Seifert, with the smooth four-dimensional genus is going to be basically the minimal genus that's allowed as the genus of a surface that your knot bounds. Okay, so this is easy to define, right? Like just wrote down the definition pretty quickly, but it's kind of hard to compute because, you know, given a knot, how are you going to find, you'd have to like look through all surfaces that it bounds, right? So there's another kind of knot invariant, which are, they're like kind of complicated to define, but they're easy to compute. I will actually define some of these quite explicitly in the next few slides, so I'll just leave this there for the moment. But the kind of non-invariant I'm mostly going to be focusing on are ones that are gauge theoretic, and they don't really fall into this. They're like kind of not so easy to define really, and also not so easy to compute. In fact, they're extremely hard to compute usually, but they're kind of useful to prove things with. So I'll sort of go into that a little bit later on. So, okay, now let's talk about these easy to define, or sorry, complicated to define, easy to compute ones. So there's the Jones polynomial. The way the Jones polynomial works is you can basically, for each, for a knot, you can draw a picture of your knot in two-dimensional space. So it's going to have some crossings, right? If you're trying to draw it on a plane, you would have to cross itself unless it's just the unknot or the unlink. So unlink and unknot, those are just the links that have no crossings. So if you take basically the Jones polynomial, it assigns a polynomial to each link diagram, but really it's invariant of the diagram, so it's to each link that satisfies this relation. So you can sort of maybe convince yourself that this actually defines, oh wait, sorry, I also have to tell you what it is on like the unlink. I didn't actually do that, but on the unlink of n crossing with n circles, it's going to be equal to well, this is not really normalized, but let's say q plus q inverse to the n minus 1. And then you have this relation if you have like these three pictures that look like this, and you can maybe convince yourself that starting with this, you can just sort of, and knowing what it is for the unlink, you can figure out what it is on every link. So here are some examples. So these are the Jones polynomials of the left-handed and right-handed trefoils. And you can see, well, okay, it's not very easy to, like, this is what part of what being complicated to define means is it's not actually easy to see that this is an invariant. Because like I defined it based on a diagram, but it is an invariant. And so from this, you can tell that like the trefoils are not the same as the unknot. Okay, but like, okay, so the sort of the knot and link invariant of this type, of the complicated to define, easy to compute type that I'm going to be talking more about is the Havanov-Lie homology. So the Havanov-Lie homology is like kind of similar. You define it based on, you start with a picture of your knot, so that in 2 dimensions, so that it has crossings. And then for each crossing, what you're gonna do is you do what's called the resolution, or you resolve the crossing in 2 ways. So that means you replace the crossing with either, like, say if you have a crossing, you replace it with either this or this. So if you have n crossings, then there's 2 to the n replacements, and you arrange them in a cube, starting with like the 0 resolution on the left, the 1 resolution on the right, and the all ones, and then for each one it's zeros or ones. You arrange them into a cube. Okay, and then there's this algebra. I sort of wrote it out, but it's just some explicit like algebra that you can assign. So for each of these pictures, once you have all the crossings resolved, then you have an unlink, right? And you count how many components are in it. So if you have like this picture, there's 3 components. So you basically want to take 3 copies of A, and then if there's 2 components, it's 2 copies of A, 1 component, 1 copy of A. So we assign like an A module to each of my pictures. And then you can sort of write down maps along the edges of your cube. And these maps are also, I only wrote down some of them, but you can also just write them all down very explicitly. So because of the way we arranged these diagrams, each edge is going to be going from like either a 0 to a 1 or a 1 to a 0 at one like place, and then at the other places it's going to be doing nothing. Because of that, it either corresponds to splitting one circle into 2 circles or merging 2 circles into 1. So what you do then is for like a merge, you can, I mean, I didn't write down all the formula because you got to be like, you know, x tensor 1, 1 tensor x, 1 tensor 1, where they all go, but this is all very explicit. You can just write them all down. So basically for each edge, you write down a differential map that either comes from a merge or a split. And then you basically compute the homology of this. This is going to be the what's called the Khovanov-Lie homology. So you take the homology of this chain complex. Okay, so this is the Khovanov-Lie homology. It's like, I guess I didn't really do this in like historical order, but for some context, it is a twisting of what's called the Khovanov homology. So the Khovanov homology is exactly the same as this, but instead of using q lambda, like these polynomials over q, in one variable, you just work over z. And in this formula, whenever you see a lambda, you just put 0. So it's like the exact same thing, but it's A is like, yeah, A is basically Z. Oh, sorry, there's still X. They still have polynomials. Okay, sorry. A is ZX. A is ZX mod X squared. The previous here, I think I might have written it wrong. The A in the Khovanov-Lie case is actually Q lambda, but you still have to do X mod X squared, right? That's why I had these X's. I don't know if like I actually explained what these X's were about. So like, so it's you're over some base ring and then you're doing Rx mod X squared. And so in the case of Khovanov homology, you're doing Zx mod X squared. So there's no lambda. And like in this formula, lambda is just 0. Okay, so that's the Khovanov homology. And so the Khovanov-Lie is kind of like a twisted version of this with this extra lambda variable. And then the Khovanov homology is it's what's called a categorification of the Jones polynomial. So like the Jones polynomial I mentioned earlier, given a knot, it gives you, or a link diagram, well, really a link, it gives you a polynomial, right? And basically if you read off the ranks of the polynomial, that's going to be, sorry, the coefficients of the polynomial, that's going to give you the ranks of the Khovanov homology. So the Khovanov homology is actually bigraded, so it's going to be like the alternating sum of the ranks along basically one of the gradings of the Khovanov homology. Okay, so that in that sense, the Khovanov homology is a category, like it basically is like the Jones polynomial, but it tells you more information. And it also, I guess I didn't actually write this down, but it's a categorification, meaning that unlike the Jones polynomial, like if you have a cobordism between knots or links, you get a map on Khovanov homology. I think that's usually what categorification means among my people, is like you have like something that originally just gives you a quantity, and now it gives you some kind of object, and you can like study maps. Okay. So a longstanding question about Khovanov homology that was resolved in 2011 was, does it detect the unknot? Meaning, if you have the Khovanov homology of K is equal to the Khovanov homology of the unknot, does that mean K is equal to the unknot? This is also an open question about the Jones polynomial, but okay, so so I think I'm gonna just define one more invariant of this kind of combinatorial nature, which is called the Rasmussen invariant. So the Rasmussen invariant, this is not the way Rasmussen defined it, but this is the way that's going to be more consistent with some other definitions we'll have later. So the Rasmussen invariant is going to be an invariant of knots that works like this. If you take, given a knot and a cobordism from the unknot to K, this induces a map on Khovanov-Lie homology from the unknot, the Khovanov-Lie of the unknot to the Khovanov-Lie of K. And then there are two generators of Khovanov-Lie homology of the unknot, and then you basically look at where those two generators go, and then the Rasmussen invariant of K is going to be twice the genus of your surface minus the number of factors of lambda in like the images of the two generators. So it's basically how many, it measures how many factors of lambda you pick up. It's going to be not very hard to check that if you add some genus, your surface, you're basically going to be adding factors of lambda. So this is an invariant. It doesn't depend on the surface, right? It's just an invariant of the knot. Okay. So here are some properties of the Rasmussen invariant. So first of all, it's additive. If you take the connected sum of two knots, the Rasmussen invariant is just the sum of the Rasmussen invariants of each. It respects mirrors. So if you take a mirror, then the Rasmussen invariant is a negative. And then the one that's sort of most central to this, like this, is the concept of a concordance invariant. So a special case of having genus, like of genus, is, remember the genus we said was if you take the genus of K, that's basically saying you have your K sitting in S3 and you're looking at surfaces in B4 and you're asking what kinds of surfaces they can bound. So unlike the Seifert surface, which I think only bounds like zero genus if your knot is trivial, this, like a knot which is not trivial, can still bound like a disk in B4. And if it does, we call that a slice knot. So slice knot is when the genus of K is zero, so it bounds a disk. And then like if in that case, if I have, this is not a slice knot, but I'm just drawing it like this anyway, because it's the only knot I know how to draw. So in that case, we can sort of think about, like, you can see your K sitting in S3, and maybe you can convince yourself that there's an annulus from the unknot to K in S3 times I. So there's a cobordism in S3 times I that goes from the unknot to K, which is a cylinder. Okay, so then this sort of leads us to the concept of concordance. So two knots are said to be concordant if they co-bound a cylinder. So a knot of genus 0 is the same thing as a knot which is concordant to the unknot. Okay, so the Rasmussen invariant, it's a concordance invariant. So if two knots are concordant, then they have the same Rasmussen invariant. So in particular, this means that if a knot has genus 0, if it's a slice knot, it has to have Rasmussen invariant 0. Okay, and actually there's like a stronger statement of this form, which is that the genus is actually bounded below by the Rasmussen invariant. Okay. So a question you can ask, this is a conjecture, is does the same inequality hold for a general homotopy form? What this means is, so I said, like, this is like talking about genus inside B4, right? The standard 4-ball. But what you can also do is you can say, okay, if I have K in S3, what if S3 bounds some other homotopy 4-ball? Then can this invariant also bound like the can it also bound genus of surfaces in that other 4-ball? And so as you might imagine, this is connected to this smooth 4-dimensional Poincare conjecture, which basically says there aren't other smooth homotopy 4-balls. So the smooth 4-dimensional Poincare conjecture says that any smooth homotopy 4-sphere is actually just diffeomorphic to the standard 4-sphere, or equivalently, a smooth homotopy 4-ball with standard S3 boundary must be the standard 4-ball. So, okay, so there's like this Friedman, Gompf, Morrison, Walker approach to trying to disprove SPC4 that basically works like this. You want to find a knot in S3, and then you want to find a surface in some smooth homotopy 4-ball with boundary S3 such that its genus is not bounded, like is not correctly bounded by the Rasmussen invariant. If you can do this, then that means that your smooth homotopy 4-ball must not be the standard 4-ball, and that would be a counterexample to, and this is like something that's like, I think I'll get a little bit more into this later, but this is like not an unreasonable like thing you could think about doing, because like you can actually just like somehow combinatorially construct homotopy 4-balls. Like there's like a whole bunch of papers of homotopy 4-balls that like of constructions of homotopy 4-balls that we don't actually know if they're diffeomorphic to the standard 4-ball or not. Okay, so now I'm going to actually talk about the instanton version of all of this. So just like a quick overview of instantons. So we're going to be talking about connections in bundles, like in principal G bundles, where G is actually just going to be SU2. I don't know why I wrote G in general, but it's SU2. And basically, like the connection is going to be like if you have a principal G bundle over a 3 or 4 dimensional manifold. Or I guess I'm writing the 4-dimensional case. So in my field, like X is always 4-dimensional and Y is 3-dimensional. It's because you count the number of endpoints. So I wrote down the 4-dimensional case, but you have a principal G bundle. You can look at horizontal, like basically ways to identify horizontal, like basically like horizontal sections. So that's like a complement of there's a vertical bundle that like very clearly what that means, right? It's the kernel of like the map down to the base. And then basically you're looking at horizontal sections, which are like complements of that. And that's a connection. This space of connections, there's various equivalent formulations, but one of them basically tells you that the space of connections is an affine space for like modeled on 1 forms with this Lie algebra. They're like Lie algebra valued 1 forms. Okay, and then we're specifically going to be considering this space of anti-self-dual connections up to gauge. So gauge is basically like you have this G bundle, you can look at G bundle automorphisms, and then if you have a connection that under an automorphism goes to the another connection, you identify those as the same. And then it's not very hard to check that anti-self-dual connections get identified with anti-self-dual connections. I didn't explain what anti-self-dual was. So if you have a connection, there's like a concept of curvature. That's basically a 2-form that you get from your connection. And then there's a Hodge star operator from like in general, in n dimensions, it goes from k forms to n minus k forms. But since we're in 4 dimensions, that's going from 2 forms to 2 forms. And so like, and recall that the curvature is a 2-form. So you can ask yourself like, what does the curvature go to under Hodge star? And we're looking for ones such that the curvature goes to negative of itself. That's anti-self. Okay, so we're looking at the space of connections up to gauge that satisfies this. These are called instantons. There's like some, I don't know, like there's some like other reasons one might be interested in instantons that I just don't really want to get into, but like you should like just believe that these are inherently interesting. But we're going to be interested in them for like a very specific reason, which is basically we're going to be using these to study 3 manifolds. So instantons are inherently a 4-dimensional phenomenon because you can only do this anti-self-dual thing in 4 dimensions. But we're using this 4-dimensional gadget to study 3-dimensional things. So if you have a 3-dimensional manifold with also a G bundle on it, then you can consider you can also do this concept of connection you can also do in 3 dimensions. That part doesn't depend on being 4-dimensional. So you can consider the space of connections on your G bundle over Y now, which is a 3-dimensional manifold. And then there's like this Chern-Simons functional. So the Chern-Simons functional goes from your space of connections. This is connections on U over Y, which is this G bundle, and it goes to, well, it actually goes to R, like I'm really gonna write it as going to R mod Z. And what we're going to do is we're gonna study, okay, so it goes from A to R, but I'm actually gonna write it as going from A mod G to R mod Z. So this is connections up to gauge. So same as in 4 dimensions, you can take a space of connections and you can quotient by these automorphisms of the bundle. And then it goes to R mod Z. And basically what we're gonna do is we're gonna want to study this space of connections mod gauge with Morse theory. So this Chern-Simons functional, you're going to think about it as a Morse function, and then we're going to do Morse theory on this space. So this is like, so usually the way Morse homology works is if you have some like nice finite dimensional manifold, then like, so you have some nice finite dimensional manifold, you can consider like some function from this manifold, which I'll call B, to R. And then you look at the critical points, right, of this manifold, and then you like you consider gradient flow lines, and you take some complex generated by the critical points where the differentials are counting the gradient flow lines, and then that's going to give you the homology, like the usual, whatever homology of this thing, because it's like it's a nice finite dimensional manifold. All the homologies are the same, and in particular, one of them is the Morse homology. So in our case, because this space is just some horrible infinite dimensional thing that's also not a manifold, because this is not like G is not actually acting on A in like a freeway or anything like that. This is just some like horrible gadget. Like this, when we do the Morse theory, we're not going to get the homology of this space, right? Because it like doesn't really make sense. But you can still just kind of do Morse theory with this. So in that line of thought, you can basically look at, so what that means is you're going to take a complex generated by the critical points of the Chern-Simons functional, and you're going to count, like the differentials are going to count the downward gradient flow. So let's talk about what the critical points and the downward gradient flows are. So you can compute the gradient of the Chern-Simons of this function, the Chern-Simons functional, and it turns out the gradient at a connection B is going to be star FB. So critical points are when the gradient is 0, which means star FB is 0, which basically means FB is 0. So critical points are flat connections with 0 curvature. And the gradient flow lines, those are, I mean, that solves this equation, right? dB dt is minus gradient of Chern-Simons, which, but this B is like a 3-dimension of like, it's like a connection on 3 dimensions, but you can sort of view it as a connection in 4 dimensions by basically looking at it as like, you have like, if you have S3 times, oh, actually this is y times r, and you have some like b of t at each time, you can put those together into a 4-dimensional connection, and then the downwards gradient flow is actually just going to be, this equation is actually equivalent to like, to the being anti-self-dual. So this star is, so like, because I think this may be a little bit confusing. This star is a 4-dimensional Hodge star, but that star is a 3-dimensional Hodge star. So these are different stars. Okay, so yeah. Okay, so this is so you do this thing that I'm saying, which is you look at the critical points, which are flat connections, and the gradient. So you look at a complex that's generated by the critical points, which are flat connections, and differentials count the gradient flow lines, which are anti-self-dual connections, right? So this is the reason I'm interested in anti-self-dual connections, or instantons. Okay, so so this is all just for a 3 manifold, but the concept I initially started this talk about was knots and links. So it turns out you can also do like basically a singular version of this to get an invariant of knots and links. Oh, sorry, I should mention that like if you do this, so what we did was we started with a manifold, any 3-dimensional manifold, and you did this. It's not actually true that it's any 3-dimensional manifold. You need to do like a few extra things to make sure that like these spaces are actually behave nicely. Like you want things like, so I said connections mod gauge in general is horrible because like the action has like, could have stabilizer and it's very bad. But it turns out that if you use manifolds that just have a slightly like some nice properties, you can make it so that flat connections mod gauge does not have this problem of stabilizers and stuff like that. Which, you know, is what your complex is actually counting. But in general, given a 3 manifold with some slight things to make it nicer, you can define this and it's going to be an invariant of the 3 manifold. I mean, I think it's not hard to believe that it's an invariant of the 3 manifold because like, we didn't really make that many. I mean, you make a little bit of choices, like you have to choose a metric in order to like, the Hodge, like to define Hodge star and stuff like that. So you need to choose a metric and you need to choose you need to choose a perturbation because usually the Chern-Simons functional is not going to actually be it's not going to be a Morse-Smale function. So you have to do a perturbation, but it's not very hard to show that this thing that you get is independent of the metric and perturbation. So basically, it's a gadget. We're given a 3 manifold. It spits out some homology, and that's called the floor homology or the instanton floor homology of the 3 manifold. Okay, so but that's like for a 3 manifold, and we started with knots and links, which are, you know, embedded one-dimensional manifolds in my 3 manifold. But it turns out you can also get an invariant of that using this gadget, where basically, if you start with a manifold, you can consider a bundle that has like a singularity at your, so you had an SU2 bundle, you consider an SU2 bundle with a singularity at your link. Yeah, sorry, K is gonna be a link in this. Like, I think most topologists like to use K being a knot, but for some reason, the people whose papers I'm referencing, they always make K a link. So you have a singularity at K, then what this means specifically is like, you're gonna choose a bundle that's sort of defined away from K, and also some arc omega that you just don't want to think about too much. And like the holonomy around your knot, so around your link K, meaning if you do a holonomy around a really small loop that goes around your link, it's going to be conjugate to I in SU2. So SU2, you can think of it as S3 sitting in quaternions. So you can think of it as unit quaternions, and there's going to be like the unit sphere in the IJK direction is basically the sphere of things which are conjugate to I. And the idea is that your holonomy around K is going to be conjugate to I. If you were actually on a bundle over all of Y without the singularity at K, then the holonomy should be 1, right? If I take a really small loop, like the holonomies should go to 1. So this is like, this kind of holonomy is basically measuring how singular you are at this knot. And then there's also going to be this other little arc that that is kind of important, but you don't want to think about it too much, but the holonomy around that is going to be -1. So your bundle is also only defined away from that arc. Okay, so this is for a 3 manifold with a singularity at a link. You can also study the same question you can put the same kind of metric on a 4 manifold with a singularity at a surface. And then basically you can do like the same theory, all of this theory, like you look at, connections on this, you look at the Chern-Simons functional, you count like critical points and gradient flow lines, and that gives you what's called the singular instanton floor homology, which is a homology of your link in your manifold. Okay, so one thing I think that might be worth pointing out is that you can sort of explicitly compute what the critical points are. So like most things in instanton homology are like very terrible to compute because like you're solving these equations in these bundles over 4-dimensional manifold, like, star of like that, like, its curvature is like anti-self dual. That's like just you're solving some like horrible differential equations and it's not good. But for the flat connections, you can kind of, in this situation, when you're like if you have a knot in S3, you can actually just explicitly compute what the critical points are by basically saying, okay, so like what are flat connections? If you have a flat connection on something, that's you can look at like the holonomies, and that basically gives you a map. A flat connection is basically defined as by a map from the fundamental group of the like not the link complement. In this case, I still have to have the complement of omega, just don't think about it too much. From the link complement to SU2. And you can sort of, I mean, so this is like the link complement, this is just like a thing in topology, like people study the fundamental group of a link complement. And so you're basically asking what is like the critical points of the unperturbed Chern-Simons functional are basically like SU2 representations of these, of the fundamental group. What do I want to say about? Oh yeah, so this is like unperturbed, which is why like you can see that this is not like usually if you have the indices right, it's supposed to be like a discrete set of points, right? The critical points are supposed to be like a discrete set of points. This is not a discrete set of points. Like if you, in general, you have some group, you're looking at SU2 representations, that's usually not going to be a discrete set of points. So this is the sense in which you do have to do a perturbation, like pretty much always. Okay. But the perturbation, it turns out you can actually just think of it as like you're adding a function on top of Chern-Simons, and you can think of it as just like a height function on whatever this representation variety is going to end up being. Okay, so yes, the instanton floor homology is this like homology that you get from like generated by flat connections, which look like this but perturbed, and you count instantons on like that go from one or agree like instantons on S3 times I that agree with one flat connection on one end and the other flat connection on the other end. Okay, so these things, it turns out, like I said, you can sort of compute explicitly what it is for what the critical points are. If you're not, or if K, your link K is just the unlink, then, oh yes, there's this other gadget you're doing where you're adding a hop link to everything. So K is this stuff. I'm adding a hop link somewhere else, and omega is going between them. But it turns out that like what this thing does is it makes it so that this, what it actually gives you is just like if you have K being the unlink, it's going to just give you a copy of S2I for each of these, right? You're like, so okay, if K is the unlink, like if you think about it, what are the SU2 representations of the fundamental group? You need to know where each meridian around each component of K goes, right? And then you also need to know where the meridian of your hop link goes, these meridians and the meridian around omega, which certainly has to go to -1. And then you're quotienting by conjugation. And it turns out what the quotienting by conjugation means is you just don't have to, you can just disregard this. Like you can choose this and this to be like, this goes to I and this goes to J. And then you're just asking each of these goes to like some element of S2I. So this variety, this representation variety is just the product of a copy of S2I for each unlink component. So for the unlink, you can easily compute what this instanton floor homology is. It's basically, it's going to be like 2 generators for each component. Then like, it turns out that the instanton floor homology, it satisfies what's called a skein relation, which is that if you have a knot, if you have 3 links that are the same outside of a ball, and in the ball, they differ like this. This is like a little bit of an asymmetric picture, but you can think of it as like, if you have a tetrahedron, basically the way they differ is you just, one of them is these 2 edges, one of them is these 2 edges, and one of them is these 2 edges. So this is actually quite symmetric, even though this picture makes these 3, one of them has a crossing and the other doesn't. But everything here, unlike the Jones and polynomial stuff, everything here is happening in 3 dimensions, right? So so if you have these three links that differ only in a four ball, and in the four ball, each of them is one of these two edges, one of these pairs of edges, then there's like an exact triangle. There's an exact sequence linking these. What that means is that there's a spectral sequence, like from this fact, this exact sequence, it's like, and like a few homological algebra facts, it's not very hard to show that there's a spectral sequence from the Havanov homology to the instanton homology. So the way that works is you can now going back to the picture of a link in 2 dimensions, you can basically resolve all the crossings. That gives you an unlink. You know what the instanton Floer homology of the unlink is, and then like basically you can sort of build up your instanton Floer homology of your original thing by basically looking at doing these exact triangles. And so these exact sequences. So that means there's like a spectral sequence where the E2 page is the Havanov homology and it abuts to the instanton homology. And so in particular, this implies that the rank of the instanton homology is bounded above, or the rank of the Havanov homology, let's say, is bounded below by the rank of the instanton homology, but instanton homology is somehow actually like it's harder to compute because it's like horrible, but like it's easier to prove things about. And it turns out like using some like geometric topology stuff, you can show that the instanton homology does detect the unknot. So because of that, Kronheimer and Rufka using all of this machinery, I mean, this paper like introduced singular instanton homology, like it wasn't just some observation. They were able to show that the Havanov homology detects the unknown. So this is like the reason instanton homology and this kind of Floer homology theory is cool, even though it's neither easy to define nor easy to compute. Somehow you can like show things with it. Okay, so this is like some story. It turns out that so this is like this singular instanton Floer homology here is an analog of Havanov homology. Basically, it sort of corresponds to Havanov homology, but it is like much more topological than Havanov homology. Like Havanov homology is like what we would call combinatorially defined, as in you start with a diagram in S3 and in S2, and then you define it with combinatorics. This thing is kind of geometrically defined. And so it sort of tells you more information about like four manifolds, like because the Havanov homology really doesn't tell you anything about any four manifolds other than B4 because of the way it's defined. Whereas this like actually tells you like, so like if, so far I've been saying not in S3 or like link K in some manifold Y, and then we're doing like, K in Y, maybe another K in Y, and I'm like saying cobordisms, and then you like can, if you have a cobordism, you can define some map from the instanton homology of this to the instanton homology of that. But it turns out that they don't have to be the same ambient manifold. So you can do like K1 in Y1 and K2 in Y2. And so now here, instead of doing Y times S1, you can just take some four-dimensional manifold, some four-dimensional cobordism from Y1 to Y2, and then you can still define like a map on instantons from this. So in this sense, it can tell you things about four-dimensional manifolds that are not just like Y times the real, no, like the real line. So it's somehow more fundamentally like a four-dimensional manifold thing than Havanov homology is. Okay, so this was for Havanov homology, but the thing I was actually like talking about first was like Havanov-Lie homology, which is this twisted thing. So it turns out you can also do like a twisted version of instanton Floer homology by looking at some local coefficients. I'm not gonna get too much into that, but basically like similarly to how singular instanton was an analog of Havanov, this thing is an analog of Havanov-Lie, and then you can just analogously define an S sharp, which is basically you do the same thing as the way we defined Rasmussen invariant, where given like a knot in S3, you can look at like a knot in S3 and then look at like the map on level of these twisted instantons, and then count like how many factors of lambda you pick up minus the genus. So that's S sharp. And so there's a few properties of S sharp. So it respects mirrors. This is like not actually very hard to show, and it's a concordance invariant. These are like all things that you can just kind of show topologically. And also it gives a lower bound for the genus of a surface. Okay, so, but one thing about S sharp that's not true or not known to be true for S is that it does bound like genus in, did I write this down? No, I didn't. It does bound genus in these homotopy fourballs, like for the same kind of reason that I was saying, that it just tells you more information about four manifolds. In general, so it bounds genus in any homotopy fourball.
What do you mean by bounds genus?
Oh, so like
That inequality there?
yeah, it's basically this inequality. So the genus here, we're only saying that, oh wait, no, I did write this down. So yeah, if you have a homotopy fourball, like, and you have a surface in it whose boundary is K, or sorry, it's a homotopy fourball with a standard S3 boundary. So if your knot bounds a surface sigma in it, its genus is bounded below by S sharp.
And the same thing is known for S without the sharp, just for standard football?
Yeah, only for the standard fourball. So yeah, so this is like, what I was saying is that, you know, you would like, if this is not true for a homotopy fourball in general, then that shows that not every homotopy fourball is a standard fourball, which would resolve the smooth four-dimensional Poincare conjecture. Okay, so some questions about S sharp that were raised was, is it equal to S? So this would kill the Friedman, Gomf, Morrison, Walker approach, right? Because it would show that like that you can't actually use S to distinguish smooth homotopy fourballs from standard fourballs. So this was actually believed to be true like for a few years, because when the paper that introduced S sharp, they actually claimed to show this, but it turns out this is not actually, their proof was not correct. So they had thought that they had killed this Friedman, Gomf, Morrison, Walker approach. And then another question you could ask is it additive? Like, this was one of the properties of S sharp, was that it's additive. And so, yeah, so, okay, one of my results in this field was I was able to show that the answer to both of these is no. So basically, I don't really want to get into this, but like this, you can define S sharp for links as well. The thing I do want to mention is that you can separate S sharp so into two different invariants, which I call S sharp plus and S sharp minus, where basically if you have a surface sigma from like the unknot to your knot, where sigma is now allowed to have both genus and self-intersection, then you can define S sharp plus minus L as the basically the genus plus the self-intersection minus the number of factors of lambda in like U plus or U minus sort of separately. And so it turns out that each of these is actually a link invariant. So you can sort of separately count the number of factors of lambda picked up by, oh, sorry, this only defined when sigma has even genus, but you can define but you can always find a sigma with even genus, right? By just like artificially adding genus to your surface. So when sigma has even genus, you can sort of separate out the number of factors of lambda in the two generators pick up, and each of those is individually a link invariant. So like I separated S sharp into S sharp plus and S sharp minus and then I was sort of able to show that if your if you have a knot in S3 that bounds a complex, like basically a polynomial, so I was saying that torus links, right, they bound like the polynomial x to the m equals y to the n. So if your knot bounds a polynomial with at least one singularity, so for example, x to the m equals y to the n has a singularity at 0. With at least one singularity, then I was just able to like just figure out what the S sharp plus and S sharp minus was. So I just computed them and they're equal to the genus and the genus minus 1. And so, oh, I guess I forgot to say this. So the S invariant for a torus knot is just twice the genus. So here we've shown that for a torus knot, the S sharp is twice the genus minus 1. So for a torus knot that's not like the unknot, which is also a torus knot, but that one doesn't bound a curve with at least one singularity. So, so for a torus knot that does bound a curve with at least one singularity, S sharp is actually going to be equal to S minus 1. So they're not equal. And you can also show from this, because if you take the connected sum of two torus knots, it turns out that also bounds a curve with a singularity. And so that means that like the S sharp of that is also twice the genus minus 1, but the connected sum, its genus is just the sum of the genuses of each. So it's certainly not equal to the sum of the S sharps of each. So that means S sharp is not equal to S, and it's also not additive. And so this sort of revived the Friedman, Gomf, Morris, and Walker approach. And so, yeah, just this. Okay, yeah. And you can also do this for links. For basically torus links, you can compute what like this S sharp is. And so I guess like I want to sort of conclude on some like recent computations that I've been doing. So since like this sort of revives this approach, the Friedman, Gomf, Morris, and Walker approach, I just want to mention that like there's been some like progress made on trying to actually do this approach. So one thing that was shown by Manolescu and Picarillo last year, or maybe 2 years ago, was that if you have two knots that share a zero surgery, meaning that like, basically this means you can like, if you take one of the knot exteriors, you drill out like along a curve and then fill in along a different curve and you get the other knot exterior, then basically, if you can show that one of them with your two knots that share a zero surgery, if one of them is slice and the other is not slice, then you can actually construct one of these homotopy 4 balls. Basically, what you do is you take the knot trace, which is like a 4 manifold coming from one of your knots, and you glue it to like the some 4 manifold coming from the other knot, and that gives you like basically a homotopy. Yeah, sorry. You take the knot trace of which is a 4 manifold coming from one of the knots, and then you basically do this surgery that gives you the other knot exterior, and then that's going to give you a homotopy 4 ball that like basically make the Friedman, Gomf, Morris, and Walker approach work, so that the one which is like not slice, you basically can show that it is slice in this homotopy 4 ball that you built. And so, but like, so some Dunfield, Obaden, and Rudd wrote a program for identifying knot exteriors. So one of the projects that I've sort of recently on and off been working on is just to try to find pairs of knots that share a zero surgery and try to figure out, this is like sort of part of a larger project, which was, this is supposed to say 19 crossings, by the way. Basically take all the knots of up to 19 crossings, for which there are like 350 million of them, and just figure out for each of these whether it is slice or not, like whether it has genus 0 or not. We were like, this is a joint work with Nathan Dunfield. We were able, out of these 350 million knots, we were basically able to like solve all of them except for like around 12,000. And then another part of the project is for one of the knots in our sample of knots of up to 19 crossings, basically try to find knots that share a zero surgery with this knot, with your given knot, and be like, basically try to figure out the sliceness, whether the other knot that shares a zero surgery is slice or not. And so like we found like 200 something thousand pairs of knots, which share a zero surgery. Like when your knot has like too many crossings, it's basically impossible to figure out whether it's slice or not, because the obstructions, basically when your knot has over like 80 crossings, it becomes essentially impossible to figure out. Like, so for most of these pairs we found, the other knot was too large to even like consider this approach, but we did have like some 20,000 pairs that where like the other knot also had less than or equal to 60 crossings, which is in the range where you can compute things like, well, you certainly cannot compute S sharp, that's not gonna happen, but like you can compute S, you can compute like, there are like various things like, there's like some other like gauge theoretic versions of S that are a little bit easier to compute, like they're called tau, and like there are various other like little invariants you can do, and you can like compute those when you have less than or equal to 60 crossings. So basically for those pairs that shared a zero surgery with our, oh, sorry, those numbers are old. This was like now more than 20,000 that had this. So we basically looked at like whether our thing had, this base slice, that means the sliceness of the one that's 19 or fewer. Other slice is the sliceness of the larger one that shared a zero surgery. And basically, we're just sort of trying to figure out. We were not able to find a counterexample to the smooth four-dimensional Poincare conjecture, but this is like the data of like what we could do with this. So for like most of our knots, like for 10,000 of them, right, we found out that neither of them was slice. For 25,000 of them, we could find slice disks for both. And then there's actually, like, interestingly, a couple, these ones, these 13 and this 3 here, where we could find either an obstruction or a slice disk for the larger one, but we're not able to do one for the smaller one. And then there's like a bunch where we couldn't figure out either. The larger or the smaller one. So yeah, that's what I want to tell you.